Welcome back. In this episode, we will be talking about a special type of random variable known as a binomial random variable. The definition is a bit involved, so rather than clobbering you over the head with it right at the beginning, I'll ease you in by discussing one specific example that can serve as our prototype for all binomial random variables. Once you've come to understand that one example, you'll be ready for the abstract definition. The example I have in mind concerns a multiple choice test. I want you to imagine a small multiple choice test, one with only 5 questions, each of which has 5 possible options. Moreover, imagine that the test is written in a language that you can't read, say Icelandic, and it concerns a subject of which you are wholly ignorant, say quantum mechanics. Consequently, you can only guess the answers at random. Now let's introduce our random variable. Let x be the number of questions that you get right by sheer luck. Okay, let's start with an easy question about x. What's the probability that x is 0? Naturally, we're going to imagine a probability tree. Our answer to question number 1 could be right or wrong, and since there are 5 options, we have a 1 in 5 chance of guessing the correct answer. That is, our probability of success on the first question is 20%, which leaves us with an 80% chance of failure. We obviously have the same 20% chance of success on the second question, no matter how we fared on question 1. We're just randomly guessing each time, so our results on the various questions are independent of one another. And the same holds, of course, for the third, fourth, and fifth questions. The probability of success is always 20%, but to avoid clutter, I haven't written those 0.2s and 0.8s on every branch. Anyway, we want the probability that x is 0, which means the probability that we get all 5 questions wrong. There's only one path through the tree that leads to this outcome, and the probability of going down it is clearly 0.8 to the 5th, which is precisely 0.32768. It's just as easy to find the probability that x is 5. The one path leading to a perfect score on the test is to go up all 5 times in the tree. Each time we go up, we pick up a factor of 0.2, so the probability we seek is 0.2 to the 5th, which is 0.00032. Very unlikely. We'll eventually build up a full probability distribution for this random variable, which I'll keep over here on another face of this box. Here we have a reminder of what x represents and an empty distribution. I'll fill in the 2 cells that we now know. If we repeat this experiment over and over, we'll generate lots of values of x, all between 0 and 5, and so far we know that about a third of them should be zeros, and that you shouldn't hold your breath while waiting for 5s. Bit by bit we'll fill in this table, but there's something interesting about this particular problem. Even before we complete the table, I claim that we can guess what the expected value of x will be. How? Just think. Since you have a 1 in 5 chance of guessing each question on the test correctly, you should get about a 5th of them right. Well, a 5th of the 5 questions on the test is 1, so it seems reasonable to expect 1 correct answer on average if we were to repeat this experiment over and over. For now, we'll just keep this as a conjecture, which we can check on once we've completed the full probability distribution. For our next entry, we'll find the probability that x is 1. This is slightly trickier to compute, since there are several paths through the tree leading to the outcome in which we're interested. Here's one. We get the first question right, but miss the others. The probability of going down that particular path is 0.2 times 0.8 to the 4th. Here's another. We could get the second question right, but miss the others. What's the probability of going down that path? It's the same as the other one. We get 1 factor of 0.2 for the one time we went up, and 4 factors of 0.8 for the 4 times we went down. Are there still other paths that lead to 1 success? Sure. Here's another. We could get the third question right and miss the others. Will this path have the same probability too? Of course it will. Once again, we're getting 1 factor of 0.2 for the 1 upwards branch, and 4 factors of 0.8 for the 4 downwards branches. And we can now make a very important observation. Every path that leads to 1 success will have the same probability, since any such path involves 1 up, hence 1 factor of 0.2, and 4 downs, hence 4 factors of 0.8. Thus, if we start with this probability, the probability of any particular path leading to 1 success, we can just multiply it by the number of such paths, and the result will be the probability that we seek. So how many paths are there that lead to 1 success? We've found 3. In one, we got only the first question right. In another, we got only the second question right. And in another path, we got only the third question right. Well, of course, there are going to be 2 more such paths. one in which we get only the fourth question right, and one in which we get only the fifth question right. Hence, there are 5 paths through the tree that lead to 1 success. We can now run all of this through our calculator and find that the probability of getting 1 multiple choice question right on this test is 0.4096. Good. Finding the probability that x is 4, that is, that we correctly guess 4 of the 5 questions, is similar. Think of any particular path that leads to this outcome. I'll start with this one, where we get the first 4 questions right, but miss the last one. The probability of going down that path is 0.2 to the 4th times 0.8, since we go up 4 times, our 4 successes, and down once. Once again, every path leading to 4 successes will have this same probability, since any such path involves 4 ups, hence 4 factors of 0.2, and 1 down, hence 1 factor of 0.8. So to find the probability that x is 4, we take the probability of going down any particular path leading to 4 successes and multiply by the number of such paths. How many such paths are there? Well, any path with 4 successes has 1 failure. That failure could occur on the first question, as in the purple path, or on the 5th question, as in the red path, or on one of the other 3 questions, which would give us 3 more paths leading to the outcome we're interested in. Hence, there are 5 paths leading to 4 successes. Thus, we have that the probability that x is 4 is 0.0064. Okay, let's record our 2 most recent results on the distribution for x. Putting them in, we find our table is now looking a little healthier. Notice how we're moving in from the outside. The outermost entries were easy to fill in. The 2 we just got required a bit more thought, and the last 2, the innermost entries, will require a little more still. Let's do it. Now we'll find the probability that x is 2. Our analysis begins the same way. We recognize that there are many paths leading to 2 successes. Here, for example, are 2 of them. Any path leading to 2 successes involves 2 ups and 3 downs, so the probability of going down any such path is 0.2 squared times 0.8 cubed, since each up, each success, gives us a factor of 0.2, and each down, each failure, gives us a factor of 0.8. Now we just need to multiply by the number of such paths. This time it isn't nearly so obvious how many paths there are, but having watched the previous video, you are now an expert in counting, so this won't be too hard for you if you look at the problem in the right way. Start with a simple observation. The 5 questions on the multiple choice test correspond to 5 vertical strips on the tree. But how does this help us? Well, we want to count the number of paths leading to 2 successes. Those 2 successes occur in 2 of our vertical strips. For example, the red path goes up in the first 2 strips, and it goes down elsewhere. The purple path goes up in the 2nd and 4th strips, but it goes down everywhere else. And conversely, if you pick any 2 strips at random, there will be a path that goes up in them and goes down everywhere else. In short, every path leading to 2 successes matches up with a pair of vertical strips, and vice versa. Thus, the number of paths leading to 2 successes is the number of different pairs of strips. And since there are 5 strips to choose from, the number of pairs of strips is, of course, 5 choose 2. All the hard work is now done, and we can punch this into our calculator, which tells us that the probability of getting exactly 2 questions right is 0.2048. It will happen about 1/5 of the time. The argument we just went through is vital for understanding how to work with binomial random variables. So to be sure that you've grasped it, let's run through it once more by computing the probability that x is 3. To find this probability, we draw, or just imagine, our huge branching tree, and we recognize that there are many paths through it, like this one, that lead to 3 successes. Just as importantly, we recognize that all such paths have the same probability of 0.2 cubed times 0.8 squared. Thus, we'll just need to multiply this probability by the number of paths that lead to 3 successes. How many such paths are there? Well, each path leading to 3 successes corresponds to a choice of 3 vertical strips from among the 5. And conversely, any choice of 3 strips corresponds to a path that leads to 3 successes. So the number of paths leading to 3 successes is the number of ways to choose 3 strips from 5, which is 5 choose 3. Put that all together, and you find out that the probability of guessing 3 questions correctly is 0.0512. Good. Let's go back to our probability distribution for x and fill in the remaining cells. Earlier, we guessed that the expected value of x would turn out to be 1. Now that we have the full probability distribution for x, we can test our conjecture. Computing the expected value in the usual way, we find that its value is indeed 1. Our conjecture was correct. As we'll soon see, this was not just a coincidence. If you've understood this example about the multiple choice test, you've understood just about everything related to binomial random variables, since every binomial random variable is like the random variable that we've been working with. To see this, let's go ahead and look at the definition of a binomial random variable. A binomial random variable counts the number of successes in a fixed number of independent trials, each of which has the same probability of success. Yes, that's a bit of a mouthful, but we can make sense of it by relating it back to our multiple choice example. In that example, we had 5 independent trials, namely 5 instances in which we guessed the answer to a multiple choice question. Each trial could be labeled either a success, we guess it correctly, or a failure, we guess incorrectly. And in each trial, the probability of success was the same, 0.2 in fact. Finally, our random variable counted the number of successes we had in the 5 independent trials. Hence, x is indeed an example of a binomial random variable. We'll consider other examples in a moment, but first I want to mention that the bi in binomial refers to the 2 possible outcomes in each independent trial, success or failure. A binomial random variable always involves this sort of thing, success or failure, up or down, heads or tails, right or wrong, etc. Conventionally, we just label one of them success and let our binomial random variable count those. Anyway, here are a couple more examples. Let x be the number of heads we get if we flip 10 coins. Is this binomial? Let's check. Do we have a fixed number of independent trials in which we are counting successes? Yes, we do. We have 10 trials, flipping the 10 coins, each of which results in something we'll call success, heads, or something we'll call failure, tails. And x, our random variable, counts the successes. Moreover, these trials are independent. There's a 50% chance of success for each one, regardless of what happens on the others. Hence, x is a binomial random variable. Let's do another example. Roughly 18% of Americans have blue eyes. Let y be the number of blue-eyed people we get if we randomly select 150 Americans. Is this random variable binomial? Well, we have to ask ourselves, do we have a fixed number of independent trials in which we are counting successes? Yes, we do. We have 150 trials in which we look at random Americans' eyes. We call all the blue-eyed Americans successes and count how many of them there are. And since the people are chosen randomly, the trials are independent. There's an 18% chance that each randomly chosen American will have blue eyes. Hence, y is indeed a binomial random variable. One reason we like binomial random variables is that their expected values are especially easy to compute. We correctly guessed the expected value of our multiple choice example, and it turns out that we can do this for all binomial random variables. It is always the case that a binomial random variable's expected value is exactly what you'd guess, namely, the product of the number of trials and the success rate. Well, this is great news, because normally we have to know the whole probability distribution of a random variable to get its expected value. With binomial random variables, this is not the case. Consider our example of the number of heads we get if we flip 10 coins. If this is x, then what can we say about the expected value of x? Well, because x is binomial, we don't have to crank out the whole probability distribution of x to find the answer. We can get the expected value just by thinking. There are 10 trials, half of which should be heads on average, so the expected value of x is 5. Similarly, let's return to y, the number of Americans in a randomly assembled group of 150 who have blue eyes. What's the expected value of y? 18% of our 150 trials should be successes, so we should expect 27 successes on average. Good. Let's do another example. Roll a die 50 times. What's the expected number of 6s? Well, if we let x be the number of 6s in 50 rolls, then x is a binomial random variable. It's counting successes, 6s, in a fixed number of independent trials, 50 of them, each of which has the same probability of success, 1 in 6. Hence, the expected value of x is easy to compute. We expect 1/6 of the 50 trials to be successes, so the expected value of x is about 8.33. Okay, now let's ask a different question about this same random variable. Roll the die 50 times. What's the probability of rolling exactly 8 sixes? Since x, the number of sixes we get in 50 rolls, is binomial, we should think to ourselves, as we should with every binomial random variable, aha, this is just like the multiple choice example. I need to imagine a huge probability tree. Note that the tree I've sketched here is just the beginning. We need to extend it further and further, much further. The actual tree in this case would have 50 branches on each path, that is 50 vertical strips, and its total number of paths would be 2 to the 50th, which is more than 1,000,000 billions. Needless to say, we cannot draw the whole thing, but that's fine. We only have to think about it. Anyway, throughout this enormous tree, every branch going up to a success, a 6, carries a probability of 1 in 6, and thus every branch going down to failure, a non-6, has a probability of 5 in 6. Once we've thought about our tree, the rest of the problem should be very familiar. To find the probability that x is 8, we first note that any particular path leading to 8 successes must involve 8 ups and 42 downs. So the probability of going down such a path is 1/6 to the 8th power times 5/6 to the 42nd power. There are, of course, many such paths with 8 ups and 42 downs. How many? By the argument we discussed earlier, there will be 50 choose 8 of them. Feeding this all into our calculator, we find that the probability of getting 8 sixes in 50 rolls is about 0.151. Here's another problem. If we roll a die 50 times, and if x is the number of sixes that we roll, find the mean and standard deviation of x. Well, the first part is easy if we remember that the mean of x is just a synonym for the expected value of x, which we already found to be 1/6 of 50, which is about 8.33. But standard deviation? The only method we know for computing a random variable's standard deviation requires us to have access to its entire distribution, which would take us all day to compute. Fortunately, we do not have to do this. One reason we like binomial random variables is that their expected values are easy to find. Another reason we like them is that their standard deviations are easy to find too. Let's put this problem on hold for a moment. You already know what a binomial random variable is, and you already know that a binomial random variable's expected value is exactly what you'd guess, namely the number of trials times the probability of success. But here's something new. A binomial random variable's standard deviation is, unfortunately, not something you'd guess, but there is a very simple formula for it. You won't be surprised to learn that this formula involves a square root, since it is, after all, a standard deviation. The standard deviation of a binomial random variable turns out to be the square root of a product of 3 things: the number of trials, the probability of success on each trial, and the probability of failure on each trial. This is a very easy formula to use. For example, go back to our question about blue-eyed Americans. Roughly 18% of Americans have blue eyes. Let y be the number of blue-eyed people we get if we randomly select 150 Americans. Then the standard deviation of y is the square root of the product of these 3 numbers: the number of trials, which is 150, the probability of success in each trial, which is 0.18, and the probability of failure in each trial, which is 0.82. Put that all together, and you get about 4.71. Anyway, let's take this new information back to the problem that we abandoned. Roll a die 50 times and let x be the number of sixes we get. We found that the mean of x is about 8.33. We can now easily get the standard deviation of x, since x is binomial. The standard deviation of x will be the square root of the number of trials, 50, times the probability of success, 1/6, times the probability of failure, 5/6. That all crunches down to about 2.64. Now, to help us develop some intuition for what this means, let's consider a related problem. You suspect a certain die is biased towards sixes. To check, you roll it 50 times, and you get 12 sixes. And the question is this strong evidence that the die is biased towards sixes? You might want to pause the video and try to answer this for yourself before I present the following analysis. Okay, let's see how you did. You rolled 12 sixes, which is more than the expected number of 8.33. In fact, you've rolled 3.67 more sixes than what you would expect if the die were indeed fair. But that doesn't tell us all that much. A better way to think about this is to ask how many standard deviations above the mean this is. Now, a standard deviation is 2.64 sixes, which goes into our surplus about 1.4 times. That is, your observation of 12 sixes was about 1.4 standard deviations above what we would expect if the die were fair. Well, 1.4 standard deviations above the mean is high, but it's not so high that we should rule out the possibility that the die really is fair and that our excess of sixes was just due to chance variation. Generally speaking, we want to be conservative about these things. We're usually hesitant to declare something fishy unless it's at least 2 standard deviations away from the mean. So although the 12 sixes may seem to confirm our suspicions, the evidence of bias is weak. This sort of reasoning, by the way, is central to inferential statistics. We will see it again. One last thing I'll mention about binomial random variables. You may have seen this sort of object before. It's usually called a Galton board after its inventor, Francis Galton. The idea is that you pour a large collection of balls into the funnel on top. These fall through a narrow opening. When a ball hits the first wedge, it's equally likely to bounce to the left or to the right. Either way, it will encounter another wedge, where again it will be equally likely to bounce left or right. After descending through 6 rows of wedges, the ball falls into one of the chambers at the bottom. Well, one question we might ask is a ball equally likely to end up in each of the various chambers? If it is, then after letting all the balls fall, the chambers should be roughly equally full. Well, to make quantitative sense of this, let's introduce a random variable. Let x be the number of times a ball bounces to the right. This might seem like a strange random variable to define, but we can connect it very easily to the chambers. Consider the leftmost chamber. The only way for a ball to get into that one is for it to go left at every stage. That is, only if x, the number of bounces to the right, is 0. Similarly, the only way for a ball to get into the rightmost chamber is for it to bounce right at every stage. That is, only if x is 6. In fact, thinking about this for a little while, you should be able to convince yourself that each chamber corresponds to a different value of x. For example, if a ball goes right 3 times and left 3 times, it's going to end up in the middle chamber, no matter where it made its right and left turns. This should remind you of our paths through those giant probability trees we've been looking at. And indeed, x is a binomial random variable. It counts the number of successes, right turns, in a fixed number of independent trials, the 6 times a ball hits a wedge, with the same probability of success each time, 50%. Having identified x as a binomial random variable, we can do all the usual calculations. For instance, take the expected value of x. Of the 6 turning points, we expect 50% to go to the right, so the expected number of right turns for a randomly chosen ball is 3. As for the standard deviation of x, this will be the square root of the number of trials, 6, times the probability of success, 0.5, times the probability of failure, 0.5 again, which comes out to about 1.22. If we wanted to know, say, the probability that x is 2, we'd think of a huge tree, recognize that any path through it leading to 2 successes would entail 2 ups, each contributing a factor of 0.5, and 4 downs, same story, so the probability of going down any such path must be 0.5 squared times 0.5 to the 4th. The number of such paths is 6 choose 2, and so the probability that x is 2 is about 0.234. We could, of course, do this for each value of x, and complete x's probability distribution, which turns out to look like this. Clearly, the chambers are not all equally likely destinations for the balls. Any given ball, for instance, is about 20 times as likely to end up in chamber 3 as it is to end up in chamber 0. There is a pleasing symmetry to the distribution, which reflects the fact that success and failure were equally likely in this binomial random variable. If we let all the balls fall, we might end up with something like this. Interestingly, this is very close to normally distributed data. Even more interestingly, it turns out that any binomial random variable, even when success and failure occur at different rates, starts to look normal if you have enough trials. This is a consequence of a result called the central limit theorem, which we'll meet later in the course. For now, I just wanted to sneak a normal curve into the last minute of this video as a preview of the next one, which will specifically concern normal random variables. That's all for now. See you next time.